Hey guys, welcome to lesson 4.4, the sum and difference identities for sine. So yesterday, or last lesson, we talked about the sum and difference identities for cosine, which you can see on your screen right here. And basically what we're going to do today is develop the sum and difference identities for sine. So to start though, we are going to use these cosine identities, and we're going to simplify what's at the bottom of our screen here, cos of pi by 2 minus a, because in simplifying that, that'll help us come up with our sine identities. Okay, so I can see that because there's a minus sign here in the argument, we're going to use the difference identity for cosine. So we'll expand just like we did in the other lesson. Cos of the first angle times cos of the second, and this time with a plus. And then we have sine of the first angle, and then sine of the second. And based on what we know about the cosine graph, we know that at pi by 2, the cosine graph is at 0. So we're left with 0 times cos A, and then plus, now think about the sine graph. Now sine at pi by 2 is 1, so we're left with 1 times sine of A. So if we go ahead and simplify this, 0 times cos A is gone, and we're just left with sine A. So here, so what we've done here is we've kind of created the complementary identities, where cos of pi by 2 minus a is equal to sine A, and it works the other way around, where sine of pi by 2 minus a equals cos A. So I'll just put that to the side there, and we can refer to that in a minute. Right now, we're going to use the cos complementary identity to help us create the sum and difference identity for sine. So moving on, we are going to simplify sine x plus y. Now what we're going to do is manipulate this just a little bit. So this argument here, x plus y, just for now, let's call that a. So really we have sine of a. And from what we did above, we know that that is equal to cos of pi by 2 minus a. Okay, so for now, let's take that a and replace it with what we're actually trying to find, which is sine of x plus y. Well, that would tell us that it's equal to cos of pi by 2 minus x plus y. And what we can do now is use a little bit of distribution, and this actually becomes minus x minus y. So for our next step, we're going to be a little tricky. We are familiar with the sum and difference identities for cosine. So what I'm going to do is group it so that we only have two terms being subtracted, that being the first term and just y being the second term. So if we focused on that and expanded with the cosine difference identity, we would end up with cos of the first times cos of the second, and then because there's a minus sign there, we'll use a plus. So plus sine of the first and sine of the second. We know that cos of pi by 2 minus x, and in our example it's an a, but it's the same thing. So cos of pi by 2 minus x is equal to sine x. And then we have times cos y. And like I said, it works both ways. So sine of pi by 2 minus x must be equal to cos of x, and then times sine y. We've actually just created the sum identity. Again, we'll take what we know and this time create the difference identity for sine. So essentially what this is sine of x plus a negative y. So now we can use what's above to expand. So it looks like we have sine the first thing, and then cos of the second angle, plus cos of the first angle, and then sine of the second angle. Now if you'll recall what we did yesterday, you'll notice that we have sines and coses with negative angles inside. So we can simplify that and say that, well, sine of x stays as is, but cos of a negative angle, as you can see on the left here, cos of a negative angle is really just the same thing as positive cos of that angle. So I can replace that with positive cos y. Now we have a cos x, and then multiply by sine of a negative angle. Now on the left side we see sine of a negative angle is equal to -1 times sine of the positive angle. So really this whole term should end up being negative, and then the angle for sine becomes positive. So we can simplify that one step further and just say sine x cos y, and then take away cos x sine y. Okay, so that is our difference identity for sine. On the next page just kind of summarizes those two identities. If you'll notice, the question says simplify the following by expressing it as a single trigonomic function. So you'll notice that we have sine of 3b and then cos b. That 3b again appears in the second term as the argument for cos, and the b appears again as the argument for sine. So really that does look like the sum expansion or the addition expansion for sine. So this is sine of the first angle plus the second angle. And we can go ahead and simplify that one step further and just call it sine of 4b. And that's it for example 1. Example 2 says evaluate each of the following and find the exact value. Okay, so when it says exact value, I don't want to see any decimals, which means you probably shouldn't be using your calculator for this. So sine of 105 degrees. What you would like to do is split up the 105 degrees into two angles that either add up to 105 degrees or subtract and give you 105 degrees. And those two angles preferably should be from your special triangles. So for example, sine 105 can be split up into 60 degrees plus 45 degrees. Now I picked 60 and 45 because those both come from our special triangles. And now that I've split it up as a sum of two angles, I can use the sum identity for sine. Again, we can reference our special triangles, and then we know that sine of 60 degrees really is √3/2, and cos of 45 is really just 1/√2, plus cos of 60 degrees is 1/2, and sine of 45 is 1/√2. So very similar to what we did yesterday, except this time you had to find the two angles that gave you the 105 degrees. So at this point we can simplify the terms. I know that when I do simplify the terms, both of them will have the same denominator, so I'll write it as just one big fraction right now. So denominators times denominators give me 2√2. Numerators times numerators is √3 plus 1. And again, we can go ahead and rationalize this. So we want to get rid of the √2, so we should be multiplying by √2/√2. And we've rationalized our denominator and got our final answer. Okay, so that first example was in degrees. The second here is in radians. You want to split up the 5 pi by 12 into two angles, both from your special triangles, that either add to 5 pi by 12 or subtract to equal 5 pi by 12. Okay, so the way I like to think about this is I kind of think about the numerator. So how can we add to 5? I know that if I had 3 pi by 12 and 2 pi by 12, that would end up being 5 pi by 12. If you look inside, you can simplify each one of these things. So sine of, if we reduce 3 pi by 12, or it reduces into an angle that is found in our special triangles. Same for 2 pi by 12. If we reduce that, we end up with pi by 6, also from our special triangles. Okay, so now we can use the sum identity for sine of pi by 4 plus pi by 6. Again, take what you know about your special triangles. Sine of pi by 4 ends up being 1 over root 2. Cos of pi by 6 is root 3 over 2. Cos of pi by 4. And then sine of pi by 6. Again, multiply them all together. You're going to get a big fraction that is over 2 root 2. We end up with root 3 plus 1. Again, if we rationalize, we actually ended up with this exact same answer in the above example, and we know that when we do rationalize, we end up with root 6 plus root 2 all over 4. Very similar to the example that we did yesterday. We are given sine of angle A as 15 over 7, and we know that sine is given to us as y over r. We also know that this angle A is in the first quadrant. We're given cos of B, given as x over r, and we know that B is in the fourth quadrant. And it's our job to find sine of A plus B and sine of A minus B. Now, as in the example that we did yesterday, we had to find a little bit more information first. We had to find cos of angle A, and we had to find sine of angle B. So let's start with the first angle here, angle A. Let's find cos of angle A. And for cos of angle A, we need x over r. Well, looking at angle A, I'm given y and I'm given r, so we need to find x. And the way we do that is with the Pythagorean theorem. So x is what we need to find. We're given y, which is 15. We're also given r, which is 17. Now, if we were to go ahead and simplify that, we end up with x squared equaling 64, and then x could either be plus or minus 8. Now, because angle A is in the first quadrant, we know our terminal arm stops somewhere in here, and we can see that any x value in the first quadrant must be positive, so we'll use x equals positive 8. So that tells us that cos of A must be positive 8 over 17. Okay, so now we'll try and find sine of angle B. For sine, we need y over r. In the question, we're given x as 24 and r as 25. So again, we'll use the Pythagorean identity. So and because in the question we said that angle B was in the fourth quadrant, we can see that any y value in the fourth quadrant must be negative. So therefore we are going to use y as negative 7, which tells us that sine of angle B is really negative 7 over 25. Okay, so now that we have all that information, I'll just recall it here for you. We can go ahead and answer the questions. So the first one was sine of A plus B. Now if we were to expand that, and because we know sine A, cos B, cos A, and sine B, we can fill those values in. So sine A is equal to 15 over 17. Cos B is 24 over 25. Cos of A is 8 over 17. And then sine of B is negative 7 over 25. We end up with 360 over 425 plus negative 56 over 425. And since we have a common denominator, we can subtract the numerators. 360 take away 56 gives us 304 over 425. And then finally for part B, which was sine of A minus B, well, again, we'll do the expansion, and you'll notice that we've already evaluated sine A and cos B. That ended up being 360 over 425. This time, take away cos A sine B, which we already evaluated as well. That was negative 56 over 425. So our final answer here would be 416 over 425. So we want to prove that sine x plus y times sine x minus y is equal to sine squared x minus sine squared y. Now in this particular identity, you'll notice that we have two different arguments, so make sure that you're very careful. So I'll start with working on the left side. Now we're going to expand. So I'll first expand sine x plus y. That is multiplied to the expansion of sine of x minus y. Basically, we have two binomials here. We can start by distributing. So we can start by distributing. First we'll do sine x cos y times sine x cos y. And that'll give us sine squared and cos squared y. Next, we are multiplying sine x cos y times negative cos x sine y. So, minus sine x cos x sine y cos y. Ends up being quite a long term. Now we'll take the cos x sine y and multiply with sine x cos y. And we actually end up with the positive version of that previous term. And then finally, cos x sine y times negative cos x sine y, and we end up with negative cos squared x and sine squared y. So the good thing about this is that the two middle terms do cross each other out. So what we're left with is, what I'll do here is just kind of pause and take a look at what we have and what we want to get to on the right side. On the right side, we have sine squared x minus sine squared y. Here's our sine squared x. I might consider doing some sort of substitution with the cos squared y. Same with the other term. I have sine squared y, which I want to keep, so I'm going to consider substituting the cos squared x. So, using the Pythagorean identity, I know that cos squared y is the same as 1 minus sine squared y. Okay, so minus 1 minus sine squared x this time to replace the cos squared x, and that's multiplied by the sine squared y. So we have two terms here, and we can distribute again. So sine squared x times 1, and then sine squared x times sine squared y. Minus, now we are going to do the distribution here, but I'm just going to keep all of our work in a bracket because eventually we're going to have to distribute this negative sign into our work. So 1 times sine squared y, and then negative sine squared x times sine squared y. And then eventually when we do distribute this negative term into that bracket, we're left with sine squared x minus sine squared x sine squared y, take away sine squared y plus sine squared x sine squared y. And again, you'll notice that terms cancel out. So we are left with just sine squared x take away sine squared y, which happens to be our right side. So we have just shown that left side equals right side. So that's it for today's lesson, and if you have any questions, please make sure you ask in class. Take care, guys.